Welcome to part 4 of the class on deep networks, number 1 in the course Artificial Neural Networks. This part 4 is about the backpropagation algorithm. The backpropagation algorithm is the most famous algorithm in the field of artificial neural networks. And yet, the backpropagation algorithm is nothing else than a smart implementation of the chain rule needed to calculate the gradient. What you see in the box is the backprop algorithm. We start by initializing the weights and then we choose patterns. Let's suppose we have stochastically selected one of the patterns from the database. This pattern is applied as the input in layer 0. Then we propagate the signal forward through the network. It goes from layer 0 to layer 1 and from layer 1 to layer 2 to layer 3 until it arrives at the output. We record the activity of the neurons in all hidden layers as well as the activity of the neurons in the output. As a next step, we calculate the error delta in the output. Then we use this information and propagate this error information backwards through the network. The delta in layer n is used to calculate the deltas in layer n-1 and so forth. This is the backward pass. And this backward pass has given rise to the name of backpropagation of errors. Then we update all the weights, not just one weight, but all the weights of all layers. And for this update, we need the deltas and we need the activations that we have calculated during the forward pass of the network. And then we go to the next pattern. I said that backprop is a smart implementation of the chain rule. But the chain rule calculation is quite complicated. So why should we go through all that effort? We are implementing everything on the computer, so why not directly implement numerical evaluation of the gradient? Numerical evaluation would work roughly like this. Let's pick one of the weights, say this one here, and then we ask how much will the error change if I change this weight either a little bit upwards or a little bit downward. So this plus epsilon minus epsilon scheme is a stable approximation of the gradient, and this allows to estimate what we want. So how would we evaluate this? Well, we need to calculate this error, and in order to calculate this error, we need to know y hat, we need to know the output, and we need to know this, and we need to know this twice, once for the plus epsilon, once for the minus epsilon calculation. Now, to keep things simple and to compare it with a stochastic online algorithm, we consider just one output pattern, which means we cut out this sum over p. So let's evaluate this error function. The error function is the target minus the actual output, so we have to calculate the output. The question is now, how expensive is this evaluation? Well, to evaluate this, we need to do the forward pass. We need to apply the pattern here. We need to evaluate the values here. We need to forward propagate further in order to get the output. So what you see is that the output has a sum over all the weights in the second layer, over all the weights in the first layer. And in fact, if you follow this over n layers, you would see each of the weights is touched in a sum exactly once. So if you just count the number of summation steps, then the order of an evaluation of the output is order n. So each weight is touched once. We need to evaluate this error function twice, but that's not very costly. It's still touched once. But then this calculation here is just for one weight. I have to change this weight here with plus epsilon and with minus epsilon. I do this estimation and I know what's the gradient for this weight. But then I have to repeat this for this weight, I have to repeat it for that weight and for that weight. So for all the n weights, to get the gradient for all the n weights, the order of the algorithm is n squared. Now let's compare this with the algorithmic complexity of the backprop algorithm. I said we have a forward pass. In the forward pass, each weight is touched once, so it's order n. Then we have a backward pass. On the backward pass, each weight is touched once. Therefore, we have order n. And then in the final step, we can update all the weights at the same time. Since we have stored in the forward pass the activations of the neurons, since we have stored in the backward pass the delta values of each neuron, we have all the information to update all the n weights. We have n weights, therefore this update is also order n. So in total, the algorithmic complexity is of order n, which means proportional to the number of weights. So let's continue with a slide, with a small quiz. Your friend claims the following. Do you agree? First claim. Backprop is nothing else than the chain rule. Handled well. Is this correct? Raise your hand now. Yes, this is correct. Second claim. Well, backprop is just numerical differentiation. Is this correct? Raise your hand now. No, this is not correct. Third claim. Backprop is a special case of automatic algorithmic differentiation. If you believe that this is correct, raise your hand now. And yes, this is correct. Implementing the chain rule in this automatic fashion is basically algorithmic differentiation. Backprop is an order of magnitude faster than numerical differentiation. If you agree, raise your hand now. And yes, this is correct. Let me summarize the lecture up to here. In the first part, we have seen that hidden neurons increase the flexibility of the separating surface that separates the positive examples from the negative ones. We can go beyond linear separable problems. We have seen the specific example of the XOR problem. Now, what shapes this separating surface are the parameters. The parameters are the weights. These weights can be adapted by gradient descent, and backprop is the implementation of gradient descent in a multi-layer network. And then backprop, like all gradient descent algorithms, converge to a local minimum, not necessarily the global one. So, big networks, deep networks, are flexible tools that can be shaped to become adaptive to different tasks, and they can be trained by backprop so as to minimize the classification error.